Lecture 1, Rotational Motion. For today's lecture, we'll be looking at the kinematics of angular motion. So for this chapter, we'll be building on the linear motion that you've done in kinematics, as well as motion in a circle in the H2 syllabus. Okay, so over here, if you recall, right, in the H2 syllabus, when we talk about motion in a circle, we actually refer to a particle that is going around in a circle. And how do we describe the motion? We describe in terms of angular displacement, your theta, as well as the angular velocity. So in this topic here, we are going to use these two terms as well, which is the angular displacement, but we use delta theta now because the initial starting displacement might not be zero. If it's zero, then theta or delta theta doesn't matter. Then we also use angular velocity, which is your omega. But we're going to introduce another new term, which is the angular acceleration. Okay, so kinematics of angular motion. Let's take a look at the first page. For the kinematics of angular motion of a rigid body, okay, firstly, let me explain what you mean by rigid body. As the name implies, okay, the body is rigid, meaning it cannot be fluid. Because in fluid, the particles are in random motion, both translational as well as rotational. So if I were to look at the neighboring particles, they will be changing all the time. So that is not a rigid body. So for a rigid body, the particles are fixed in space. Solid would be a very good example because in the solid, right, the molecules are more or less fixed and the neighboring particles are always the same. Okay, they are only in vibrational motion. There isn't any translational or rotational. So a rigid body is a body, okay, that's the definition, that can rotate with its part locked together and without any change in its shape. So for a rigid body, right, if you take a look at a particular point, then you describe the motion for that point, you find that when I talk about angular displacement of that point, it will be same for the other points. Since the rigid body, so if one point displaced by theta, all the other points will also be displaced by theta. Okay, that is to say the angular velocity also the same. If one point is moving at an angular velocity omega, all the other points which are fixed are also moving at the same angular velocity. Then we are only doing fixed axis of rotation, meaning when the rigid body rotate, right, the axis will not change. It is always about the same axis. So with that, let's take a look at the terms that we use to describe. This one I will just quickly go through. Firstly, let's take a look at the body. So in figure 1, you see a rigid body, the shape of an egg. So the axis of rotation here is Z. Then there should be 3 axes, right? X and Y will be here. So to describe the motion, we need to describe in terms of theta, right, omega. So what we can do is we choose a reference line. With this reference line will be where I measure my angular displacement from. There is a condition for the choice of the reference line. It must be at 90 degrees to the rotation axis. Okay, so it will be along the same plane as your x and y, but need not be parallel. Okay, it can be anywhere as long as same plane as x and y. So if you were to look from the top, so if you look from the top, see this is your z-axis. The axis of rotation is perpendicular to the page. Then you have your x and y. So if my reference line is here at an angle theta, okay, so see it's in the same plane as x and y, but at angle theta respect to x. So the initial displacement, right, at time 0 is theta. Okay, so that is your theta naught initial displacement. So how do we describe motion? We can talk about the position. Where is it respect to our reference line? So as you can see in figure 2, with respect to our reference line, okay, the particle is here. Then how do you find or relate your angular position to arc length or radius. So from geometry, we know that theta equals to arc length S over R. So if the theta is small, your arc length is approximately the displacement. Okay, next let's take a look at the angular displacement delta theta. Angular displacement, as the name implies, is the change in the angular displacement. So that will be the final, let's say theta 2 minus theta 1 in figure 3. Let's suppose that at time t1, okay, the angular displacement of your reference line is theta 1, measured from x-axis. Then for time t2, angular displacement is theta 2. Then the angular displacement in the time interval from t1 to t2 will be given by theta 2 minus theta 1. So how do you define the next term, angular velocity? This is the same way as we define linear velocity. Linear velocity is the rate of change of displacement. So angular velocity, you just add in the word angular, it will be the rate of change of angular displacement. So instead of S2 minus S1 for linear velocity, we change it to theta 2 minus theta 1, which is the angular displacement over the time taken. So this will give you the average angular velocity. If you limit the time to approximately 0, okay, so what you are finding will be the angular velocity at that instant, which is the gradient of the tangent at that time. Angular velocity is a vector, so the direction that we're taken to be positive will be the counterclockwise or anti-clockwise direction. So this is sign convention. Okay, then clockwise will be taken as negative. Angular acceleration, oh by the way, angular displacement also is a vector because it's a displacement. So same thing, anti-clockwise positive, clockwise negative. Then the next term, angular acceleration, alpha. This is a new term, we don't do it in H2 physics. So for angular acceleration, also same is a vector. Also same, we are taking anti-clockwise to be positive and clockwise to be negative. So the way we define angular acceleration is the same as linear acceleration. Okay, just that we replace the velocity, change of velocity by change of angular displacement. So you have theta 2 minus omega 2 minus omega 1. That will give you the average angular acceleration. To find the acceleration at a certain time t, which is the instantaneous acceleration, angular acceleration, you find the gradient of the tangent. Okay, so you make the time interval very small. The next section, so we're done with how we describe rotational motion. We use theta for delta theta. We use omega as well as alpha. So now in the next section, we're going to look at what happens if the acceleration is constant. So we are looking at constant angular acceleration. Just like in linear acceleration, when it's constant, we can look at the equation of motions. So rotational also, we look at the equation of motion. So if you refer to table 1, which is on page 30 of your lecture notes, you will see the equation side by side. So I'm going to bring you to page 30. Okay, I'm putting the equation at the back so that it's easier for you to refer. You need to refer it every time in case you cannot remember. So for the left hand side, you see the linear motions. These equations here, the 4 equations of motions, you can use when you have constant linear acceleration. So what happens when you have constant angular acceleration? Same thing. Okay, you replace v by omega, u, which is the initial velocity, by omega naught. Then you replace s by angular displacement. S is the linear displacement. A, linear acceleration by alpha. Okay, then you get the 4 equation of motion for angular motion. How you derive them? It is the same as how you derive these 4 equations for the linear motion. So you can plot the ST graph Okay, from the gradient you get the v, so that's how you come up with the first equation. Same thing for this equation in angular form. You plot the displacement distance graph, then find the gradient. So all these four equations for the angular motion are derived in the same way as your linear motion. Okay, now we go back. Sorry, there's testing of the speaker. Okay, so there will be some disturbance. Okay, now we take a look at work example 1. In work example 1, you are given a green stone rotate at constant angular acceleration. So constant acceleration, so we know that equation of motion come in. Alpha is positive, that means alpha is in the counterclockwise direction. At t0, initial velocity omega naught is minus 4.6. That means initially it's going in a clockwise direction. The reference line is here. Okay, theta naught is taken to be 0. Okay, you might like to pause, take some time to do your work example 1. I'll go straight to the solution. Okay, in A, you're asked to calculate the time after t equals 0, where the reference line is at angular position theta equals to 5 revolution. 5 revolution would mean there is a total displacement of 10 pi, angular displacement of 10 pi. So using s equals to ut plus half a t squared in the angular form, my s will be 10 pi, omega naught minus 4.6, alpha 0.35. So the time taken is 32 seconds. Okay, in part B, you're asked to describe the motion. So there are a few parts to it. Let me go through one by one. So firstly, we know that at the start, it is rotating in a clockwise direction. Why? Because your omega naught is negative 4.6. But the angular acceleration is positive. Okay, so that means there will be a deceleration. So the greenstone will be slowly rotating and eventually change direction. So that's the next part. So the initial opposite sign of the angular velocity minus 4.6 and the angular acceleration, which is positive, means that the wave will slow down and eventually stop before reversing to the positive direction, which is the counterclockwise. Then after that, you will expect the reference line, okay, to pass through the initial orientation, that is a theta equals to 0, and eventually move another 5 more revolutions at t equals to 32 seconds. Okay, let's take a look at C. You're asked to find when it stopped. So using the fact that when it stopped, velocity is 0, so angular velocity is 0. So sub into the equation, you get time to be 13 seconds. With that, we're done with example 1. Now let's take a look at example 2. Okay, here we are talking about a rotor, which is a thin part right, cylindrical in shape. You spotted passenger in acute distress, so you decrease the angular speed from initial omega naught of 3.4 to final omega 2. Total displacement, angular displacement, 20 revolution. And your total is constant angular acceleration. So all the equation of motion come in. What is the constant angular acceleration? So I have omega naught, I have omega, I have the angular displacement. So I use this equation of motion where alpha is the only unknown. From there I solve my alpha. So minus 0.0301. So this is very similar to doing kinematics in linear motion. Okay, let's take a look at part B. How much time did the speed decrease take? So I have omega naught, I have omega now, I also have alpha. So this is the equation I will use. Split in, time is 46.5 seconds. Okay, the next section 1.6, right, we will be looking at how the linear quantity is related to the angular quantity. From H2 physics, under circular motion, we know that S linear displacement equals to r theta. We also know that V Okay, the linear velocity will be equal to r omega. And this is something new, the last one, the angular acceleration multiplied by the radius. This will give me the tangential acceleration, which is the linear acceleration. Okay, this linear acceleration is the same direction as your linear speed tangential if the acceleration is positive. If the acceleration is negative, then the tangential acceleration is opposite to the direction of the linear speed. Okay, so in H2 physics, our tangential acceleration is always zero because we do uniform circular motion, meaning the speed, okay, of the particle moving in a circle is a constant. So when we do a rotational motion with tangential acceleration, we will have to be very careful because the linear acceleration now will have two components. Okay, so what are the two components? One, of course, will be the tangential acceleration, which is at 90 degrees to the radius. Then the other one is the centripetal acceleration. Centripetal acceleration is a linear acceleration because it's always pointing in a straight line towards the center of the circle. So that is a linear acceleration. So when we talk about non-uniform circular motion, that is when the tangential acceleration at is not zero, we will have to be very careful because the linear acceleration will be the resultant of your centripetal acceleration and your tangential acceleration. Okay, these two are at 90 degrees. So if you want to find the resultant, you just take the vectorial sum, which you can find by using Pythagoras theorem. Okay, with that, let's take a look at work example 3. Very long question. Okay, let me go through the question with you. You're asked to design a track, okay, for an induction roller coaster. So the acceleration right throughout the motion is caused by the magnetic forces, as mentioned here. To create the initial thrill, each passenger is to leave the loading point. So this is the loading point with an acceleration g along the horizontal track. Okay, so the track before the loading point. So by the time it comes to the loading point, you're told the acceleration is g. Then to increase the thrill, the next section of the track is a circular arc. So this is for one circular arc, so that there will be a centripetal acceleration. So as the passenger accelerates along the arc, the magnitude of this centripetal acceleration increases alarmingly. When the magnitude A of the net acceleration referring to the net linear acceleration, which is the resultant of your tangential acceleration and your centripetal acceleration. Okay, when it reaches 4g at the point P, and theta P along the arc, we want the passenger then to move in a straight line along the tangent to the arc. So after that, it go in a straight line. So let's take a look at part A. You're asked to find theta P. So to find the arc length, okay, let's take a look at what info we have. We have the net acceleration. Okay, so I want to find theta P. Theta P must come from your equation of motion because that is the only equation that gives you displacement, angular displacement. So to do that, okay, we look at what we have. We have tangential acceleration. By the time I come to a loading point, you're told that the linear acceleration is g. The net acceleration when it reaches p is 4g. So the net acceleration at the point P is given by the vectorial addition of the centripetal acceleration AR and the tangential acceleration. So sub in AT as G and A net as 4G, I'll be able to find the centripetal acceleration, which I call the radiant acceleration because it's along the radius. It will be root 15G. Okay, then to use this equation to find delta theta, right, I will need to know what is alpha. How to find alpha? Well, I have a centripetal acceleration. I can find omega. Okay, before we find alpha, we must find omega because this equation omega. So if I take the centripetal acceleration divided by r, that will give me my omega squared. So this one done. Initial angular velocity is 0 because by the time I come to P, it is just at the start of the circular motion. Okay, so angular velocity is 0. Alpha, how to find alpha? Alpha we know is linked to the tangential acceleration. Remember the table in the previous page? Page 5, this one. Tangential acceleration, okay, this one. And your angular acceleration is linked by r. So I recall this equation, at equal alpha. So my alpha is just at over r. Okay, at over r is g, because at is given in the question as g. So that will be g over r. So theta p is the only unknown. So from there I get the angular displacement theta p. And then part B, what is the magnitude of the passenger's net acceleration at point P and after point P? So net acceleration will be referring to the resultant of AT and AR. So at P, right, it is still moving in, at P, it is moving in a straight line, okay, no, come out of the circular arc. So there's no centripetal acceleration. So it will just be moving at the tangential acceleration G. Oh, sorry, that's after P. Okay, after P. Then what about at P? At P is the end of the circular arc. So there is still centripetal acceleration. So the A net, right, will be just 4g given the question. It is after P, no more centripetal acceleration. So the net acceleration is just AT, the tangential acceleration, which is g. So with that, we come to an end for lecture. Thank you.